Hi students, welcome to the Section-Rupture-Bolted lectures and welcome to the design of steel structures, limited method, IS 800, analysis and design of tension members, right? In which we will see in today's class design of lug angle, right? These are the lug angle which is connected to the main angle, right? These are lug angle connected to the main angle to one side of a gusset plate. Right? In the previous class, we have seen in the design of tension members, the strength of tension members with welding connection like this, right? One problem, as well as the tension member splice design like this, second problem. I hope you enjoyed the discussions there. If you have really enjoyed, then don't forget to click like, share, subscribe and comment to our YouTube channel. Now let us see the brief profile of the speaker. That is mine. I, Dr. D. Rupesh Kumar, has obtained my BTech Civil Engineering from Nagarjuna University in 1994 and MTech Section Engineering from JNTU Hyderabad in 2000 and PhD Section Engineering from JNTU Hyderabad in 2009. Presently, I am working as Associate Professor in Department of Civil Engineering, University College of Engineering, Hyderabad, Telangana State. Right? I have an experience of 27 years, of which 7 years is in industry and 20 years is in teaching and research at graduate, postgraduate levels. My research areas include reinforced cement concrete design, steel structural designs, structural analysis, point element analysis, earthquake engineering, bridge engineering, and structural optimization. I have published 45 research papers in national and international journals and conferences, organized 3 international conferences and 11 national conferences as well as workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures, edited 3 books, supervising 14 PhD scholars and supervised 30 ME theses. Right? I am actively involved in various consultancy works that are offered by the department and completed over 750 design proof checks and 150 designs of RCC, steel, composite, low-rise as well as high-rise multi-stored buildings and road and rail bridges. Right? Once we see this brief profile, student, let us see what we'll be discussing in today's class. Right? This is how, right? Lug angle, right, which is connected to the main angle like this, right, to one side of a gusset plate, right, like this, right. And this design will be seen, right. If need be, then only we'll design this lug angle, right, which is connected to the main angle, right. And this is how the front view, student, right, as a lug angle which is connected to the main angle, right. Or I'll also show the other schematics, right, like this. This is how the main angle to which a lug angle is connected to one side of a gusset plate. Or let us see, this is also another view, right. This is a main angle, right, main angle, wherein if there is a restriction on this overlap of this, overlap, then only will be designing this lug angle, right, lug angle. Otherwise, if there is no restriction, they will not design the lug angle, right. Now let us see a numeric problem, then you will understand, right. Now this is how that lug angle will be connected to the main angle, right. Now let us see, this is also another schematic, right, where this is the main angle, right, to which a lug angle is connected, right. Therefore we can see that even both are connected, even to the top of the main angle leg to the top of the gusset plate, as well as the lug angle connected leg to the top of the gusset plate, as well as the outstanding legs of this main angle as well as lug angles are also connected by means of bolts, right. These designs we will see, student, right. And another schematic view, right, there is a main angle is connected by means of a lug angle, right, and which is connected by means of 4 bolts here, right, as well as the main angle is connected by means of 5 bolts, as well as we can see that the outstanding legs of both the angles are connected by means of 4 bolts, right. These 4 bolts also, right, to one side of a gusset plate, right. These 2 angles are connected back to back to one side of a gusset plate, this gusset plate, right. And this is just the 3D schematic, student, right. Front elevation, gusset plate, and this is a lug angle and the main angle, right. I hope you understand, right. This is just I am showing simply that of a main angle connected to one side of a gusset plate. However, if at all it is failing in block shear criteria, how it is failing, that I will see in during this problem, right. That is how it will be failing in tension as well as the shearing criteria simultaneously. Block shear criteria, that is how the shear, right, tension failure as well as the shear failure. These problems will see, student. Now let us move quickly to the top, the lug angle design, student, right. Now this is how in today's class we shall see the design of lug angle, right, conforming to IS 800 2007 class 10.12, page number 83. Let me just go to page number 83 of this IS 800 student, right, page number 83, right. Yes, I am there in page number 83 of IS 800, right, page number 83 of IS 800, right, wherein now the code says that the lug angles are connecting outstanding leg of a channel shaped member shall be as far as possible disposed symmetrically with respect to the section of the member. Obviously, right, that is it should be disposed symmetrically with respect to the section of the member, right, so as to avoid the eccentricity. The next codal specification is in the case of angle members. In the case of angle members, the lug angles and their connections to the gusset, gusset or other supporting member shall be capable of developing a strength not less than 20% in excess of the forces in the outstanding leg of the member, in the outstanding leg of the main member, right, and this outstanding leg of the main member. However, the attachment of the lug angle to the main angle shall be capable of developing a strength not less than 40% in excess of the force in the outstanding leg of this lug angle, right. Now the next codal specification is that in the case of channel members, if at all I do have the channel member instead of this angle student, right, like this, if I do have a channel member, right, if I do have a channel which is connected to, right, the gusset plate, right, gusset plate, then in such a case, right, like the lug angles and their connections to the gusset plate or other supporting members shall be capable of developing a strength not less than 10% in excess of the force not accounted by the direct connection of the member, and the attachment of the lug angle shall be capable of developing 20% in excess of that force, right, 20% in excess of that force, right, that is how. And even the next specification is that in no case fewer than two bolts shall be used, right, not less than 2 bolts, rivets or equivalent welds shall be used for attaching the lug angle to the gusset plate or supporting members. That we'll see during designs, right. And the next specification is the effective connection of the lug angle shall be as far as possible terminated at the end of the members connected, right, and the fastening of the lug angle to the main member shall preferably start in advance of the direct connection of the member to the gusset or the other supporting member, right. This we'll see during the detailing, right. The final codal specification is that where lug angles are used to connect an angle member, right, the whole area of the member shall be taken as an effective notwithstanding the requirement of the class or section 6 of this standard. Means there the class 6 is not applicable, right, the entire gross area itself is the effective area. This is important codal specification, student, right. Once we examine these codal specification, let us move to numeric problem, student, right. Numeric problem of design of lug angle. If need be, we will be designing the lug angle, otherwise we will just design the main angle itself, right. Now let's see the numeric problem, right. A diagonal member of a roof truss carries a service pull of 300 kilonewton, right, like this, right. Design the section and its connection with 16 mm thick gusset plate. The length of the gusset or connection is limited to 340 mm. This is how that restriction is there, 340 mm, right. Design the lug angles also if required, like this, right. Design the lug angle also if required. This lug angle also if required. This is the main angle, right, if required, right. Use Fe 410 grade steel as well as 4.6 grade bolts. Right? This is how the problem given, student, right. Now let us see the given data, right. Right, what is the data given here is Fe 410 grade steel is given. Therefore ultimate strength of the steel is equal to 410 Newton per mm square, and yield stress of the steel is equal to 250 Newton per mm square, and partial safety factor, right. If I go to this table 5 of IS 800 2007 page number 30, in the previous class also we have seen that partial safety factor, right, for the ultimate stress gamma m1 is equal to 1.25, whereas the partial safety factor for the yield stress, right, gamma m0 is equal to 1.1 respectively, right. These we already know, right. And also Fe 410 grade 4.6 grade bolts are given. Therefore, if I go to this table 1 of page number 13, let me go to that page number 13, right? There, page number 13, student, of IS 800. Just wait for a moment, right? 13, right? Therefore, I am there in that page number 13, student, right? Now, from this, I do have for FE 4.6 grade bolt, right? Ultimate strength of the bolt, ultimate tensile strength is equal to 400. From this, table 1 of IS 800 2007. Therefore, I just noted down that, and the yield stress is equal to, is nothing but that 400 multiplied by this 0.6. It now works out, say FYB is equal to 240. And also from the same table 5 of page number 30, I do have, let me go to that page number 30, student, right? Page number 30, right? Therefore, that is 30, right? Yes, this is how that page number 30, right? I do have this partial safety factor against, right? Gamma m0 is equal to 1.1, right? And whereas gamma m1 is equal to 1.25, just now we have seen that, right? Even the bolts, for the bolts, right, for shop fabrication 1.25, right? Whereas for field fabrication also it is 1.25, right? And the bolts in bearing, gamma mb is equal to 1.25. Then also in either in bearing or that of the bolts in friction, in both the cases is 1.25. Therefore, I am just noting down that value as 1.25. Therefore, gamma mb is equal to 1.25. For this ordinary black bolts, we are designing using ordinary black bolts of grade 4.6. right? Now let us see. Here we will see the designs in 3 parts, right? First one is the design of this main angle, student, right? Design of this main angle, right? Once I propose a section to the design of this main angle, then what I'll do is I'll also propose, right? I'll also propose the number of bolts required to connect this main angle to that of this gusset plate, right? Gusset plate, right? That is in the subcomponent of the design, right? Subcomponent of this design, right? And once I do that, then I come to know what is the exact cross section detail, student. Then immediately I'll check for the design tensile strength whether it can carry the required design tensile strength or not, right? That is the next step. That if it is okay, then I'll also check check from both, right? From rupture strength point of view as well as the block shear strength point of view. If it is okay, then I'll say that that section is my final section, right? That is how the first component design, right? Then I'll go to the next component design as the design of the lug angle, right? That is how the design of the lug angle also, right? This second component design, right? This second component design, lug angle design, right? If it is okay, if the proposed section is okay, then I'll propose the number of bolts, right? That is how the second component design should. Now let us see. I hope what we are going to do. Now. Let us see in the form of a numeric substitution, student, right? That is how now I'll initiate the first subheading as the design of main angle. The design of main angle, right? This main angle, right? However, what is given in the problem is the service load is equal to 300 kilonewton. Therefore, the factor design tensile force is equal to 450 kilonewton, because the partial safety factor for dead load and level load is equal to 1.25. Therefore, that 1.5 multiplied by 300 kilonewton service load or working load, working tension is equal to working pull tension is equal to 300 kilonewton. Therefore, it works out say 450 kilonewton. Therefore, now once I know that, then how much of now if I go to IS 800 2007 class 6.3.3 page number 33, let me go to that page number 33, student, the quicker pace, right? Page number 33, right? Just bear for a moment, right? I am there in that page number 30, right? I am now there in page number 33, yes, right? Because this is a single angle, right? Or actually it is other sections also, right? Because this main angle is connected to, if at all it is connected to the lug angle, then these are the two angles connected to one side of a gusset plate, right? If at all it is required. Otherwise, it is a single angle connected to one side of a gusset plate, However, even in other case also, other sections means TDN of double angles or channels and I sections, etc., shall also be found out using the same equation 6.3.3 as if that of the single angles. Therefore, now right, that is how as per this single angles, right? Wherein now we will see that in single angles for preliminary sizing, the rupture strength of the net section TDN is equal to alpha AN FU divided by gamma M1, where alpha is equal to, let us say, I am assuming to start with I will be requiring 4 or more number of bolts. I am just assuming because the load is already 450 kilonewton, student. Therefore, predict that I require more than 4 number of bolts. Therefore, alpha is equal to 0.8. Therefore, if I substitute that, now TDN is equal to 0.8 AN F divided by gamma M1, right? Gamma M1, right? Therefore, I'll recall this formula. Now, I'm just substituting here. Therefore, substituting here. From that, the required net area, A net required is equal to T divided by 0.8 gamma M1 divided by FU. Therefore, substituting the numeric value is 415 10 to the power 3 multiplied by 1.25 divided by 0.8 multiplied by 410. I require 1715 mm square. 1715 mm square, because this alpha is equal to 0.8, because I am going to use this is my assumption that I am going to use more than 4 number of bolts, right? Therefore, now I require net area is equal to 1715 mm square. Therefore, always for this net area, in order to get this gross area, you increase the area by 25 to 50 percentage, right? 25 to 50%. It is better you increase by 50 percentage if more load is there. Here more load is there, it is better you increase by 50%, but I am just proceeding with that of 25%. But later on we can check that it may not be okay. It may not be okay to take this 450 kilonewton. Therefore, it is always better you increase by 50%. If you don't want to optimize. However, if you just want to optimize the section, then you start with first trial with the 25%, then slowly you may increase to some next 40%, or in the third trial you may go to 50% if you really want to optimize. Here I want to optimize the section, therefore I want to proceed with 25%. Therefore, the gross area required, AG required, is equal to 25% extra than that of this net area 1715. Therefore, now I require 2144 mm square. 2144 mm square is the gross area required. However, now let us try with ISA 150 by 75 by 10 mm angle, connected to one side of a gusset plate, right, like this, right? Therefore, if I go to this SP61 1964 table number 4, page number 14. Let me go to that SP61 table 4. Page number 14. Yes, I am there in this, right? ISA 150 by 75 by 10, right? For which we can see that the gross area of this angle section is equal to 2156 centimeter square. 2156 mm square, or 21.56 centimeter square. Therefore, I am just recalling that value from SP61 1964 from table 4 of page number 14, from page number 14. Therefore, I just noted down that. Therefore, now I know this value, gross area is equal to 2156, but this is just greater than the required 2144 mm square. Therefore, it is okay. Primarily, you may simply proceed if you want to optimize. Otherwise, if you don't want to do repetitive calculation, you will simply proceed with 50% increase, right? That is all. Now, once I say this has the main angles which is connected to one side of a gusset plate, student, right? Gusset plate like this, right? Then I want to, right? This is how the schematic, student, right? I'm just proposing this ISA 150 by 75 by 10 as the main angle which is connected to this one side of a gusset plate. I am showing the front elevation as well as, right, side elevation, as well as this is the front elevation, right? This is the front elevation, student, like this, right? This is the front elevation, right? Like this, right? This is the outstanding leg. This is a connected leg to this gusset plate. This gusset plate is 16 mm thick. This gusset plate is 16 mm thick, right? Therefore, this is how this connected leg is equal to 150 mm. Now you can see that this is 150 mm, right? 150 mm is the connected leg, whereas this outstanding leg is equal to 75 mm, right? That is how my assumption, right? Then once I do this, then what I'll do is I want to do, right, the bolted connection, right? How many number of bolts are required, like this, right? Either 1, 2, 3. How many number of bolts are required? How many number of bolts are required to connect this main angle with that of the gusset plate? Therefore, now I initiate the design of the bolted connection, right? Assuming, because this data is not given, I'm just assuming the nominal diameter of this bolt, right? D or pi is equal to 20 mm, student. Therefore, then if I go to this IS 2007 page number 19, page number 73, right? Table 19, page number 73. Let me go to that page number 73, student, right? 73, right? Then yes, this is how that page number 73. I am there in the connection, right? Because my diameter is equal to 20 mm, student, which is in between 16 to 22. Therefore, from table 19, assuming standard clearance holes, the diameter of the hole, this diameter of the hole should be 2 mm more, 2 mm more, the top this, right? Therefore, now the diameter of the hole is equal to DHR, right? DH is equal to I'll get 20 plus 2. 20 plus 2 is equal to 22 mm, and as well as from IS 1367 part 3 2002 page number 9, the net, right? Let me go to that, right? Page number 9, right? I am there in that page number 9 of, right? This is a page number 9 of IS 1367 part 3 2002, right? There I do have M20 will have this nominal stress area, right? Or at the threaded section, like this, at the threads, right? This is equal to 245 mm square. However, if you don't want to remember that, even what you can do is that can be obtained. A and B is approximately equal to 0.78 multiplied by the gross area. Gross area is equal to pi by 4 20 square. Therefore, 0.78 multiplied by 314. It is 245 mm square. Right now, next one. Also, from this class 10.2.2, page number 73, from page number 73 of this IS 800, student. Let me go to that page number 73, right? Yes, this is that from page number 73. The minimum spacing, the pitch should not be less than 2.5 times the nominal diameter, as well as the maximum spacing shall not exceed 32 T or 300. If it is a tension member, right, that maximum pitch should not be more than 16 T or 200 mm. We are designing a tension member, therefore 16 T or 200 mm, whichever is less for the tension members, right? Now, as well as that of, right, now as per that, now I'll say that yes, pitch should not be less than 2.5 times nominal dia, therefore it should not be less than 2.5 multiplied by 20, 50 mm, right? As well as from the same same page, next Codal specification says that the end distance in the direction of the this one, right, shall not be less than 1.5 times the whole diameter in case of rolled machine flame cut or sawn or planed edges. Therefore, generally we will be using the punching machines to have these holes. Therefore, it is machine flame cut or sawn, right? Therefore, 1.5 multiplied by the whole diameter. Therefore, now I do have the whole diameter is equal to 22. Therefore, edge distance should not be less than 1.5 multiplied by 22, not less than 33. Therefore, R say 40 mm, right? This is how my assumptions, right? This is how that pitch, right? This is how just assume that this end distance is equal to 40 mm and the pitch is equal to 50 mm, right? The distance between these two is equal to 50 mm, and this end distance, right, here to here, this end distance is equal to, right, 40 mm, right? Therefore, once I fix this, now what I'll do is, now I'll check, right? From this class 10.3.3, page number 75. Let me go to that page number 75, student, right? Let me go to that page number 75. Yes, and there in that, therefore, these are the normal or ordinary bolts or bearing type bolts, right? Wherein, as per this class 10.3.2, I do have, right, VDSB, design strength of the bolt. VDSB is equal to VNSB divided by gamma MB, right? Where VNSB is a nominal shear capacity of the bolt given by FUB divided by root 3 multiplied by NN plus ANB plus NS ASB, right? Therefore, substituting into this, now you can please see that, right? Here the main angle is connected to one side of a gusset plate only, therefore there is only single shear. This is under single shear, right? Therefore, this is under, these bolts are under single shear. This is a single shear, right? Therefore, now the strength of the bolt in single shear is equal to VDSB is equal to, right, substituting the numerics. Now I would have 400 divided by root 3 multiplied by single shear, 1 multiplied by 245 divided by 1.25, that divided by 10 to the power 3. It works out 45.26 kilonewton upon division by 10 to the power 3, right? Now I'll get 45.26. You can simply remember for a single shear for 20 mm dia, right? The strength of the bolt is equal to 45.26, right? 45.26, right? Now, however, if you want to calculate the number of bolts, you require bolt value. Therefore, in order to get that bolt value, what now I need to do is, then I need to find out the strength of the bolt in bearing. Therefore, now I'll go to this next class 10.3.4, page number 75, student. The same page, right? For ordinary black bolts, it says that VDPB is equal to VNPB divided by gamma MB, where VNPB is equal to nominal bearing strength of the bolt given by 2.5 kb DTFU, right? Where kb is the smaller of these four values: 1 E divided by 3d0, 2 P divided by 3d0 minus 0.25, 3 FUP divided by FU, and 4 is equal to 1, right? 1, right? Where T is the summation of the thickness of the connected plates considered. Therefore, now let me substitute into this, right? Therefore, I am recalling that where KB is given by those four criteria from this page number 75. Therefore, I already fixed what is edge distance. Therefore, from the first criteria, right, E divided by 3d0, 40 divided by 3 multiplied by 22, it works out 0.606, student, right? From the second criteria, P divided by 3 multiplied by 22 minus 0.25, it works out 0.508, right? From the third criteria, FUB divided by FU, right, 400 divided by 410, it works out 0.975. The fourth criteria is 1. Therefore, out of this, whichever is minimum. However, you can see that 0.508 is the minimum, right? The second criteria. Therefore, I'm recalling this, and now I'll substitute into this, right? Therefore, the design bearing strength of the bolt, in bearing, right? In contact surface along the periphery. In bearing, right? Therefore, it now is equal to VDPB upon substitution, right? 2.5 multiplied by 0.508, because KB is equal to 0.508 and D is equal to 20. Where T, however, what is T? T is the thickness of the main angle. Thickness is equal to 10 mm, and that of the gusset plate is equal to 16 mm, right? Therefore, out of these, right, the main angle will fail first in bearing, in contact bearing, it will fail first. Therefore, T is equal to 10 mm. Therefore, I'm just recalling that, right? Therefore, T is equal to 10, that multiplied by FU is equal to 410 divided by 1.25, that divided by 10 to the power 3. It works out, say, 83.31 VDPB, right? Design bearing strength is equal to 83.31. Therefore, now I'll get the bolt value. Bolt value is equal to B is equal to least of the strength of the bolt in single shear as well as that of the in the bearing criteria. Therefore, which are respectively 45.26 or 83.31, right? Therefore, because it is in single shear criteria, that value will govern as 45.26. Therefore, B is equal to 45.26 kilonewton. Hence, the number of bolts required using this formula, bolts required, N required is equal to factor the tensile force divided by bolt value. Therefore, substituting into it, now I'll get, right, 450 divided by 45.26. Now I'll get, say, 9.94, or say 20 mm dia bolts, 20 mm dia bolts, right? Now, however, if I put 20 mm dia bolts in one single row like this, what will happen, right? Let me show like this, right? Then what is that? Now, like this, right? If I provide just in one single row, student, right? In one single row like this, right? Or like this, right? In just one single row, right? Right? Whether that length of this overlap, is it okay or not, right? That now I'll check. Right? Therefore, let me check this. What is this length of this overlap, right? Or however, that length of the gusset plate should not be more than that. That specification is given, right? That restriction is there. Therefore, then length of the gusset plate required, L required, is equal to between all these 10 number of bolts, 9 pits are possible, right? Like this, right? 50, 50, 50, all this, right? And two edge distances, right? Here one as well as here at the other end. Therefore, it works out 530 mm. But in the problem, it is given that the length of that connection or that of the gusset plate should not be more than 340 mm, student. Therefore, it is not okay. This length cannot be more than 340 mm. Therefore, now if that is a restriction, there is no other option but to design for a lug angle. Therefore, I am just concluding that hence a design or provide a lug angle. It is a compulsion now. It is a must. Then only a lug angle is required. Otherwise, if if there is no such restriction, let us say this value is equal to 330, which is less than 340. Therefore, you need not provide a Lug angle. You need not provide a Lug angle, student, like this, right? There is no requirement of a Lug angle in such case, right? However, there is a requirement of the Lug angle now. Lug angle must be provided because there is a restriction. 530 is greater than 340. It is not acceptable. I don't want to provide, right? Therefore, I need to design this Lug angle. Hence, now I am saying that out of these 10 number of bolts, provide 620 mm dia bolts connecting main angle leg with the gusset plate, like this, right? 1, 2, 3, right? 1, 2, 3, 4, 5, right? 6. These six number of bolts. 1, 2, 3, 4, 5, 6, right? And then rest of the bolts are 4, right? These 4 number of 20 mm dia bolts, right? Connecting the connected leg of the Lug angle with that of the gusset plate. These are the 6 number of 20 mm bolts, right? These are the rest. 10 minus 6 is equal to 4 number of 20 mm dia bolts, and 4 20 mm dia bolts for connecting the Lug angle with that of the gusset plate, as shown in this figure. Right? That is how the figure, student, right? That is how the figure. Just I am showing this figure, student, like this, right? Connecting the main angle, to that of the gusset plate, right, with 6 number of 20 mm dia bolts as well as 4 number of 20 mm dia bolts. Now, therefore, the length of the gusset plate required in such a case, what will happen is that, right, I have to have 6 number of bolts. Therefore, 5 pits are there, right? 5 multiplied by 50, and 2 exit distances, 2 plus 40. Now it works out 330. It is just, you can see that it is just less than 340 mm. Therefore, okay. Therefore, from this end to the other end, it is just 330 mm, which is, however, the restriction is this length is given as 340 mm. Therefore, 330 is just less than 340 mm. Therefore, additionally, I have just 10 mm extra, right? Therefore, it is okay. Therefore, once it is okay, then I'll say that okay. Means I have concluded that I need to design the Lug angle. The next subheading, right? Before I go for this design of this Lug angle, student, what now I'll do is that I'll check, because I already provided some section ISA 150 by this main angle, right? ISA 150 by 75 by 10 mm as the main angle. Now, whether it can resist this 450 kilonewton or not. Therefore, there is a next subheading, right? Check for design tensile strength of the main angle is the next subheading, right? However, now what I'll do is, if I go as per this class IS 800 2007 class 10.12.6 page number 84, just now we have seen that the gross area itself is net area. Therefore, no other check is required as per this class 6, right? Therefore, you need not that gross area itself is net area. Just now we have seen in the starting of this discussion. Therefore, no other check is required for deduction of these holes, for calculating the net area, right? Nevertheless, we'll once again check, right, with the deductions also, right? Therefore, now what I'll do is that respecting that Codal specification, now as per this class IS 800 2007 class 10.12.6 page number 84, right? Let me go to that page number 84, student, right? Let me go to that page number 84. Yes, 84. I am there in page number 84. Yes, as per this, right? This code says that when Lug angles are used to connect an angle member, the whole area of the member shall be taken as effective, notwithstanding the requirements of the section 6 or class 6, right? Therefore, however, gross area itself is net area. But now what I'll do is, right, now respecting that Codal specification, now I'll check, right, as per this class 6.2 page number 32, right? Let me go to that page number 32, student, right? Page number 32. Yes, I am there in page number 32, student, right? Therefore, this is right, not this one, right? Page number 32. Yes, this is that Codal specification, right? Design strength due to yielding of the gross cross section, right? TDG is equal to AG Fy divided by gamma m naught, right? Substituting into this numeric values, now I'll get, right? Therefore, now I do have the design tensile strength due to yielding of the gross cross section. TDG is equal to the gross cross section is equal to 2156 and Fy is equal to 250 divided by 1.1, that will be 10 to the power 3. It now works out 490 kilonewton, which is greater than 450 kilonewton. Therefore, it is okay, right? As per the code, if you just check this, this is okay, right? This is okay as per this class 6.2. But nevertheless, what now I'll do is, assuming that these are just normal angles connected, connected like this, two angles connected to one side of a gusset plate, just normal angles, right? That check as a lug angle is over, student, right? But nevertheless, even if I check two angles connected on one side of two angles back to back connected on one side of a gusset plate like this, right? One side of a gusset plate, even if I check, what will happen, right? If this angle, whether this angle can take 450 kilonewton factored load or not, that now I'll check, right? Though it is not required as per the Codal specification, I'll check, right? Therefore, for which now what I'll do is, now the second check, it is okay in yielding of the gross cross section, it will not yield. Therefore, right, now let me also check, right, whether this is the check for the design rupture strength as per this class 6.3.4, page number 33. Let me see that Codal specification, student, right? In the same page, this is the design strength due to rupture of the critical section. This is not that plate, student, right? Right, this is not that plate, right? This is a single angle, right? Actually, the rupture strength of an angle connected through one leg, right? Through one leg, right? Like this, right? Through one leg, right? Is affected by the shear lag. Then TDN is equal to 0.9 ANC Fu divided by gamma m1 plus beta AGO Fi divided by gamma m naught, right? Therefore, where beta is equal to 1.4, 0.076 W by T Fi divided by Fu, BS divided by LC, it should be less than or equal to Fu gamma m naught divided by Fi gamma m1. However, this value beta should be greater than or equal to 0.7, where W is the outstand leg width, right? This one, right? Outstand leg width, right? And BS is the shear lag width, as shown in this figure 6. Now we'll see this, right? Therefore, this is if it is connected by one bolt here, right? Here, this distance, right, is nothing but this W1 plus W minus this thickness, right? That is how the Codal specification. If it is connected by means of the bolts, right? Therefore, now once we see this Codal specification, student, then what I'll do is, then I'm just wide opening, right, this angle. If I just open, right, open like an angle is open, right? This is how just an angle, right? Angle, if I open, that will become, right, like a plate, right, like this, right? Therefore, let me show this, right? Therefore, this is that angle. Previously it was an angle, right? Right? If I just open, right, it will become like a plate, like this, right? Therefore, where it has, right, the bolt, right, lines, right, bolt lines are there, right? With however, the assumption is that the bolts are provided in staggered pitch, right? This is out that staggered pitch, right? PS is equal to 50 divided by 2, 25 mm, right? Or I need to find out this gauge distance. Therefore, for which I need to go to the Codal specification SP61. What is this gauge distance, right? Therefore, now I'll do that one, right? Now, however, once I open this, right, then now it becomes, right, let me go to this SP61 1964 table 31, page number 168. SP61, page number 168. Just wait for a moment, right? Page number 168, student. Let me go to that page number 168. Or this one, student, page number 168. Yes, this is that, right? Is the table 31 rivet gauge distances in legs of the angles from ISI handbook for structural engineers steel sections, SP61 1964, table 31, from page number 168, from page number 168. Therefore this is how, here what is shown is that if the bolts are to be provided in 2 rows, therefore what should be this distance A? What should be this distance A, starting from the root end of the root radius, right? And also what should be this distance from this central line of this first bolt line to that of the second bolt line, this B, if all the bolts are provided in 1 row. If all the bolts are provided just in one row, then what is this distance C? What is this distance C from the end of the root radius? That is also given. Therefore now I do have the connected leg. The connected leg is 150. Therefore for 150, if I want to provide just in one row, then you can see, right, then C value is equal to 90, right? 90, right? Like that, right? Even similarly, if the connected leg is equal to 75, right, then it should be 40. It should be 40, right? Like that. If I note down these numeric values, student, then just recall that, right? Therefore, as per this code, this value, right? This value is equal to 90 mm, right? This value is equal to 90 mm, right? That is what given this, right? This value is equal to 90 mm, right? Then what is that rest of the length? Rest of the length is equal to, right? Because this is 150 minus 90, it now works out 60 mm. This from the central line of this bolt to the end of the up to the end of this toe, up to the end of this toe, it works out up to the end of this toe. From this to the end of the toe, it is equal to 60 mm. It is equal to 60 mm. Therefore now I know that, right? Whereas this length of the outstanding leg is equal to 75 mm. However, just now I've seen that for 75 mm, right, if I want to provide in one row, right, it should be at a distance of 40 mm. That Codal specification also showed, right? This 90 mm, right, as well as this 40 mm, I have just noted down from the Codal specification from SP61, right? This as well as this, right? Therefore, if this is 40 mm, then 75 minus 40, then rest of the distance is equal to 35 mm, right? Therefore, that is how it is connected to one side of a gusset plate, right? Then if it is wide open like a plate like this, then what is the total width of this plate is equal to, right, this 150 plus 75, 225 minus this thickness 10. Therefore it now works out, right, this distance is equal to 215 mm, right, is the length of this plate, like a plate, right? It is actually angle, but it is acting as if a plate, right? And this distance we already seen as 20 mm, student. Then from central line of this bolt to that of the next central line of this bolt, right, this second row, right, this distance is equal to how much, right? The distance is equal to 90 plus 40, 130 minus 10 mm. Therefore it is equal to 120 mm, right? This 35 mm is equal to this 35 mm. Therefore from this end of the second row to the end of the toe is equal to 35 mm, that we already seen, right? That is how. And this pitch is equal to 50 mm, that we already seen, right? Therefore the staggered pitch PS, right, means this distance from the center of this hole to the next center of this bolt in the staggered pattern, PS is equal to 25 mm. Even this is also 25 mm, right? And now as per this, now I have gauge G is equal to the distance between these two is equal to gauge 120 mm. Therefore once I know these, then what I'll do is that I'll go to this Codal specification, wherein I do have the failure patterns are either like this. The failure may occur along 1, right, either 1, right, or it may go to 2, then come to 3, then 4, or second pattern is 1, 3, 4. 1 3 4. Therefore in both of these patterns, now I'll find out what is the net area. Therefore the net area along this 1 3 4 means if this is splitting along purely along this splitting failure, right, 1 3 4, then the net area along this 1 3 4 is equal to, right, 215, from which only one direction, from only one direction of the hole, 22 mm, that multiplied by its thickness is equal to 10 mm. Therefore it works out 1930 mm square. Whereas if the splitting is occurring along 1 2, right, 3 4, 1 2 3 4, then the net area along that is equal to, right, 215 minus two directions are there, right, 22 mm. However, during which one staggered pitch, right, it is crisscrossing by one staggered pitch, right, summation or I is equal to 1 to n, right, one pitch, right, divided by 4g. 4g is equal to 4 multiplied by 120. 4 multiplied by 120, right? Therefore that multiplied, that is a effective width, that multiplied by thickness 10. It works out, say, 1723 mm square. 1723 mm square. However, this is just greater than that net area provided, 1715 mm square. Therefore okay. Once it is okay means even further no check is required as per this Codal specification. As per this class 6.2, even further no check is required, but nevertheless I'll simply proceed, right? Simply proceed with further checks, right? Saying that then what is the design tensile strength due to rupture of this net cross section, right? Then it now works out, right? It now works out, say, TDN, right, as per this class 6.3.3. Let me show that, right? Let me show that class, right? As per this class, right? 0.8. TDN is equal to 0.8 AN FU divided by gamma M1, right? Therefore, substituting into which now we'll get, right, TDN is equal to 0.8. Just now we have seen that net area out of this 1930 as well as 1723. 1723 is the least, therefore that multiplied by 410 divided by 1.25 divided by 10 to the power 3. It works out 452.12 kilonewton, which is just greater than 450 kilonewton. Therefore it is okay. Further, as per the code, no further check is required. However, along this 1 2 3 4, the design strength due to rupture of this net cross section is just greater than. That's why I told student, right, in the design, this is the optimized design, right? This is the optimized design what we have started with 25% excess. If you don't want to optimize, simply you can increase the grass area by 50%. Just greater than 450 is greater than, just greater than 450 mm. Therefore okay, right? Okay. Otherwise, if it is less than, then another iteration is required. Therefore it is okay, right? Then, however, these further checks are not required as per the code. These further checks are not required as per the code, but nevertheless I am proceeding with these checks, assuming that, right, even if this is acting as if two angles connected back to back of a gusset plate, then what is that what is that tensile capacity, tensile strength of this main angle section, right? Therefore now I do have this shear lag width BS is equal to W plus W1 minus T, where W is outstanding lag, this 75 mm plus this 90 mm, right? Therefore this 90 plus this 75 minus 10 mm, it is equal to 155 mm, and the distance between the end bolts LC means, right, this to this is LC is equal to, now I do have, right, phi multiplied by 50 mm, right, it is equal to, right, 250 mm student from that figure. Therefore beta is equal to, right, 1.4 minus 0.076 minus 75 divided by 10 upon substitution, multiplied by 250 divided by 410 multiplied by 155 divided by 250, it works out 1.185. However, as per the code, it should be less than or equal to Fu divided by Fi multiplied by gamma M0 divided by gamma M1. Therefore, substituting with, now I'll get 410 divided by 250 multiplied by 1.1 divided by 1.25. It should be less than or equal to 1.44. Simultaneously, it should be greater than or equal to 0.7. You please see that, right? This value 1.185 is less than 1.44, this value, as well as it is just greater than 0.7. Therefore okay, means this beta is equal to 1.185. It is okay. Therefore Once I get this, now what I'll do is I'll calculate what is the net area of the connected leg. A and C is equal to 150. This 150 is punctured by one bolt hole, 22 mm minus 10 by 2 multiplied by that thickness, 1230 mm square. Similarly, now code says that it should be treated as the outstanding leg should be treated as the gross area itself, right? Therefore, the gross area of the outstanding leg AGO is equal to 75. But nevertheless, I am even making a deduction of sorry, I am taking that as a gross area itself, student, without any puncture, right? Therefore, 75 minus half the thickness, right? 70 multiplied by 10, 700 mm square, right? That of the gross area of this outstanding leg. Though there is a bolt hole provided, code says that it should not be considered. Gross area should be considered as the net area. Therefore, no net area. Net area itself is the gross area, right? Then, therefore, now I have to have this design strength due to rupture of this net section, right? Let me see this formula, student, right? As per this, now I have to have this formula, right? Just now we have seen that formula, right? TDN is equal to 0.9 ANC Fe divided by gamma m1 plus beta AGO Fi divided by gamma m0. Substituting the numeric values into this formula, now I will get, right, TDN is equal to 0.9 1230 multiplied by 410 divided by 1.25, right? 1.185 multiplied by 700 multiplied by 250 divided by 1.1, that whole divided by 10 to the power 3. Now I'll get 551.62 kilonewton. This is much greater than 450 kilonewton. Therefore, okay, means the design strength due to rupture at the net cross section is much greater than 450 kilonewton. Therefore, it is okay, right? Now let me also check the next one as the check for the block shear strength. Check for the block shear strength as per this class 6.4.1, page number 33. Let me see that code specification at a quicker pace, student, right? Like this is how the design strength due to block shear for bolted connection. I do have the bolted connection now. Therefore, the block shear TDB is equal to ABG Fi divided by root 3 gamma m0 plus 0.9 ATN Fu divided by gamma m1 is the first criteria. The second criteria is equal to TDB is equal to 0.9 ABN Fu divided by root 3 gamma m1 plus ATG Fi divided by gamma m0, where AVN, AVG, AVN are the minimum gross and net area in shear along bolt line parallel to 1, 2 and 3, 4. 1, 2 and 3, 4 in this first figure are parallel to 1, 1, 2 in the second figure, right? And the second one is ATG and ATN are the minimum gross and net area in tension from bolt to hole to toe of the angle or end of the bolt line perpendicular to the line of the force, means along this 2, 3 in this first figure as well as 2, 3 in this second figure, right? In this second figure, let me show this schematically, student, right? Now like this, right? Like this, not this one, right? I'll show this one, right? Yes, this one, right? Along this, right? Therefore, this is 1, 2, this is 2, 3, right? This is 1, 2, this is 2, 3, right? 2, 3. Then after failure of this block in shear criteria, then this block will come under the simultaneous action of the tension at this as well as the shear failure along this plane, right? Like this. I'll also show another schematic like this, right? It will fail simultaneously under the action of the tension of this plate, right, between these two holes as well as under the shearing criteria, right? Therefore, this entire block will come out under the block shear criteria like this, right? Therefore, under tension as well as the shearing failure, right? Then let me substitute into these, right? Therefore, I have to have the numeric values. Now once I see this, right, now I hope you understood what we are trying to do, student, as per this class 6.4.1, page number 33. Just now we have seen, right? Therefore, where AVG is equal to, substituting into that, now I have to have, right, 5 multiplied by 50 plus 40. You have, please see this, right? Therefore, 5, this distance is equal to 5. AVG is equal to 5, 1, 2, 3, 4, 5 plus this one ended distance, that multiplied by thickness is equal to 10, right? 2900 mm square, whereas AVN net, right? Out of this, now you please see that, right? Whereas if it is failing in shear criteria, you please see that here 1, 2, 3, 4, 5 number of bolts will totally participate, whereas this sixth bolt will only participate by 50%, because the rest of the 50% will go along 2-3 line, this 2-3 line, right? Therefore 5.5 bolts will be participating. Hence the AVN is nothing but that same 5 multiplied by 50 plus 40 minus 5.5 multiplied by 22 is the net width multiplied by thickness 10 mm. That works out 6090 mm square, right? Now next one, ATG means what is this? What is this distance, right? 60 mm, right? This, right? 60, from which half the deduction need to be deducted. Therefore now I would have ATG, right? Gross area along this line, along the tension line 2-3 is equal to 60 multiplied by 10, 600 mm square, whereas ATN is equal to 60, half the bolt deduction like this, right? 60 minus half multiplied by 22 multiplied by 10 is equal to 490 mm square. Once I get this, now I'll substitute in this formula, student. Just now we have seen this formula, right? TDB1, substituting which now I'll get, say, 2900 multiplied by 250 divided by root 3 multiplied by 1.1 in the denominator plus 0.9 multiplied by 490 multiplied by 410 divided by 1.25, that whole divided by 10 to the power 3. Now I'll get 525.17 kilonewton under first criteria, whereas even there is a second criteria, right, given by this formula, right, as say 0.9 AVN 1960 multiplied by 410 divided by root 3 1.25 plus ATG 600 multiplied by 250 divided by 1.1, that whole divided by 10 to the power 3. It works out 424 kilonewton only, right? Therefore the tensile, the block shear strength is least of these two, 525.17 or 424.41 kilonewton. Therefore the minimum is 424.41. if I am checking under block shear criteria, it is just less than that factored tensile force of 450 kilonewton. Therefore it is not acceptable. Though the code is not recommending to do this check, I am assuming it to be just a single angle connected to one side of a gusset plate, right? Therefore it is just less than 450 kilonewton. Therefore it is not acceptable. Therefore it is not okay. That's why I told you, consider the gross area as 50%, then it should be okay. But if it is not okay, then what even you can do without redesigning also, what I can do is that by changing this this distance from the end of this toe to the top of this bolt line, from increasing this distance from previously it was 60 to now 90 mm. I want to increase by 90 mm. Previously this distance was 90, this distance was 60 mm. Now I am just reverting them, right? Therefore I am just making this, I am swapping 60 to 90, 90 to 60. Therefore I am just swapping these values like this, right? Previously this was 60. I am just making this as 90. Therefore this 90 will become 60. Therefore swapping these values, obviously the area ATG will improve. Therefore ATG is equal to now this 90 multiplied by 10, 900 mm square, whereas ATN is equal to 90 minus half, 22 multiplied by 10, 790 mm square. Therefore now if you substitute into this first formula TDB1, right, into this, now instead of 525, now you will get a value. You can recalculate on your own, student. Therefore it works out 613.73 kilonewton, right? Now similarly, by substituting into this second formula, right, 0.9 AVN FU divided by root 3 gamma m1 plus ATG FU divided by gamma m1. Previously I got 424.4. Now if you substitute these new numeric values, now you will get 492.58. Therefore the block shear strength is least of these two values, 492.58 kilonewton, which is greater than 450 kilonewton. Therefore it is okay. Right? Just by changing, you please see that by changing this distance from 60 mm to 90 mm, one alternative. Or alternatively, what you can do is you can increase this pitch value also. That is the second alternative, right? Second alternative. That is the important point, right? Alternatively, what you can do is either you can increase both the pitch as well as this end distance from the toe, both. Third alternative. Or alternatively, you can increase the grade of the bolt, or alternatively even you can you can increase the grade of the steel. The third criteria is increase the grade of the steel. Right? It has nothing to do with the bolt, student, right? Therefore, increase the third one. What you can do is increase the grade of the steel, right? Therefore, because once increasing the grade of the steel, Fi value as well as Fu value both will increase, right? That is how then you can check this. But now I am okay by changing from 60 to 90 mm. It is okay. Therefore, hence provide ISA 150 by 75 by 10 mm angle as a main angle, connected by means of 6 20 mm dia bolts connected to the main gusset plate, like this. Main gusset plate in single row, like this, right? Like this, right? I'm just now showing these 6 20 mm dia bolts are like this. 1 2 3 4 5, these 6 number of bolts, right? That is how the design of the main angle, and it's a connection, student, right? Connection, right? Once I do that, now what I'll do is, now I need to design the lug angle, because it's already concluded that design of the lug angle is required. Therefore, now I'll initiate the next design of lug angle. Therefore, now let me calculate what is the gross area of the connected leg of the main angle, right? Therefore, I have to have this main angle is connected leg is 150 mm, from which now I'll deduct the half the thickness. 10 by 2 multiplied by its thickness is equal to 10 mm. Therefore, it works out 1450 mm square, and that of the outstanding leg 75, right? The gross area of this outstanding leg of the main angle is equal to 75 minus this 10 by 2 multiplied by this 10 mm. It works out 700 mm square. Therefore, the load taken by this outstanding leg of this main angle, outstanding leg, is equal to, because its area was 700 divided by that 700 plus that of that connected leg, right? 1450 plus 700 in the denominator, that multiplied by 450 kilonewton is taken by this main angle, 450. Therefore, that is how that outstanding leg will take its due share as 146.5 kilonewton only, right? Therefore, once I see this, we already seen these Codal specifications as per this class 6.4.1, page number 33. Let me go to that page number 33, student, right? Page number 33, right? Yes, I am there in page number 33. Page number 33. Yes, right? Now I have to have from this page number 33. Page number 33, right? There we have seen that the design tension member, just wait for a moment, right? This is as per this page number 83, student. I'm sorry, right? From page number 83, I'm sorry, right? Therefore, I'll go to that page number 83. Therefore, let me go to that page number 83. Just wait for a moment. 83, 97, right? Therefore, yes, I am there in that page number lug angles, right? Just now we have seen that in case of angle members, the angle and their connection should to the gusset angle, gusset plate and supporting member shall be capable of developing a strength not less than 20% in excess of the force in the outstanding leg of the member. Yes, and also the attachments, means the bolts of the lug angle to the main angle shall be capable of developing 40% excess of that force in the outstanding leg of this angle, right? Therefore, I'm just recalling this once again, these Codal specification. Therefore, I just recall that, right? Therefore, the design tension in the lug angle is equal to 20% excess of that of this 146.5 kilonewton, which is 175.8 kilonewton. Therefore, now let me calculate the net area of the lug angle required. Even just now we have seen for the main angle also the same calculation, student. Therefore, TD, because it is I am assuming that here also we already concluded that lug angle is also connected by means of 4 number of bolts. Therefore, alpha is equal to 0.8. Therefore, now I do have TD is equal to alpha multiplied by FU divided by gamma m1 multiplied by AN. Therefore, AN required is equal to 175.8 divided by 0.8 multiplied by 10 to the power 3 multiplied by 1.25 divided by 410. It works out 670 mm square. 670 mm square. That of this main angle design is over. That of this lug angle. Therefore, now I do have, you also require the net area of this lug angle. This lug angle, student, right? 670 mm square. That of this net area of that of this lug angle, not that of this main angle. This is the main angle. This is that lug angle. Therefore, if you require this one, therefore obviously I don't want to take any risk. In the previous case also that section failed. Therefore, let us provide the gross area by 50% more. Therefore, 1.5 multiplied by 670, 1005 mm square. That of this lug angle, right? Therefore, let us try. What now I'll do is, already the outstanding leg is 75 mm. Therefore, I'll take the same ISA 150 by 75. That of the main angle, its thickness was 10 mm. But now for the lug angle, I'll take its thickness as just 8 mm, because I don't want to take any risk of failure of this lug angle, right? Failure of the lug angle. Therefore, now I'm choosing a section ISA 150 by 75 just by 8 mm. Main angle was 10 mm. Therefore, if I see that SP61, I already showed that now the gross area is equal to 1742 mm square, right? Let me go to that, right? Not this one, student, right? This is how that SP16, right? Right, this angles, right? Yes, unequal angles, right? Unequal angles. ISA 150 by 150 by 150 by 75, 150 by 75 by 8 mm. Therefore, for which 1742 mm square. 1742 mm square is the gross area. 1742 mm square is gross area. However, just I require 1005 mm square only. Therefore, it is okay. But even now, let me check if means the only difference is, right, here. Now this length is, instead of 215, it will become, right, 150 plus 75 minus 8 mm. This will become, instead of 215, it will become 217, as well as the gauge distance. Instead of 120, it will become, right, 120, it will become 90 plus 40 minus 8. That is how the change in the gauge length will become 122. Therefore, that is how these are the changes. Whereas the crack patterns, once again, because they are protruded in staggered pattern, student, either it may fail along, right, either 1 3 4 or along 1 2 3 4. These both we have seen for the main angle also. The same is also applicable for the lug angle also, right? Therefore, the net area along this 1 3 4 just now I have shown, right, 217. Now this, if at all it is opened, right, this angle is opened, then that total length is equal to 217, because this is equal to 150 plus 75 minus 8 mm, that will work out 217, from which if one deduction is there, 22 mm, that multiplied by its thickness is equal to 10 mm, then it works out 1560 mm square along 134, crack pattern along 134. Whereas if at all it is failing along 1 2 3 4, then 1 2 3 4, this one, right, 1 2 3 4, right, 1 2 3 4, in which case I am encountering one staggered pitch of 50 mm as well as a gauge distance of 122, right? Therefore, I am just recalling that, right? Therefore, along that, the net area is equal to AN 1 2 3 4 is equal to 217 minus 2. Two deductions need to be done there. You please see that, right? Two deductions are there, multiplied by one staggered pitch of 25 mm square divided by 4G 122 mm. Substituting that multiplied by thickness 8 mm. Therefore now I'll get 1394 mm square, which is much greater than the net area required is equal to 670 mm square. Therefore, as per the code, even further no check is required. No check is required as per this Codal specification. Therefore, I'm just skipping off. Even if you are further interested, you may do the checks like this, right? Therefore, check for the design tensile strength as we have done for the main angle, right? Even for one check is that on the gross cross section yielding, as well as the net the rupture of the net cross section, right? As well as that of the third one is the check for the block shear, but that is not required because we already provided much area, gross area, almost roughly 75% more, therefore it will not fail. Therefore I'm just skipping up that check further. And even as per the Codal specification, that is not required. Therefore now I'll go for the next subheading as the bolted connections. Therefore the now as per this class 6.4.1, just now we have seen that the bolts should be capable of taking 40% more strength. Therefore now I'll say that, right, the number of bolts required to connect the lug angle to the top of the gusset plate N1. However, that force just now we have seen that it is equal to 175.8 kilonewton divided by, obviously, even this lug angle is under single shear. Therefore, the bolt value for this lug angle is also 45.26 only, because it is in single shear. However, in bearing it will not govern. Therefore, 45.26 is the bolt value. Therefore, now N1 will work out. Say N1 will work out 3.88. R say approximately 4. That we already told. Even in the previous case also 4. Right? That is okay. Right? Even we already concluded that provide 4 number of bolts. Right? Whereas the next one is the number of bolts required to connect the lug angle to the outstanding leg of the main angle. These bolts, student, right? These bolts, just wait for a minute, right? These designs, right? These bolts which are connecting the outstanding leg of the main angle with that of this lug angle, right? These bolts, right? Now these bolts I am trying to do that connected that of the outstanding leg of this main angle with that of the outstanding leg of this lug angle. These bolts, right? These bolts I am trying to design. Therefore, now the code is saying that these must carry 40% more than that of the strength in the outstanding leg of the main angle. Therefore, that is also the Codal specification. Therefore, now I'll say 1.4. The force in that bolted connection should be 1.4 multiplied by this N2 is equal to 1.4 multiplied by that force is equal to in the outstanding leg is equal to 146.5 multiplied by 1.4, 40% extra divided by the bolt value is equal to 45, because this is also there in single shear. Therefore 45.26. It now works out N2 is equal to say 4.53 or say 5 number of bolts. Right? That is how. Now I'll show schematically, right? This like this, right? Therefore just now I got, right? Therefore provide 420 mm dia bolts, right? Like this, 1 2 3 4, connecting the lug angle, connecting the lug angle to the top of the gusset plate, student, like this here, right? Connecting the lug angle, connected leg of the lug angle to the top of the gusset plate. Whereas also provide, right, 5 number of bolts connecting the outstanding leg of the main angle to the top of the outstanding leg of the lug angle. These 5 number of bolts, these are 5 number of bolts are required, right? In as shown in figure, right? If I see in the front view, these are in one row. There are, right? Now I'm showing this, right? Therefore 1, right, 2, 3, right, 4, 5, right? The same I'm showing in front elevation, right? I'm showing in front elevation, right? That is how the bolted connection, student, like this, right? The bolted connection. the bolted connection, right? Like this. This is how the lug angle, student, right? By 4 number of bolts, right? Here 6 number of bolts are there, whereas these are 5 number of bolts, right? These are, once again I'm saying, right, these are 6 number of 620 mm dia bolts, right? These are 420 mm dia bolts, right? Whereas these are 520 mm dia bolts. Therefore I'm showing the front view, side view, as well as the 3D view, as well as the schematic, right? This is how the schematic, final schematic, right? Schematic, student, right? That is how the design of a lug angle, student, like this, right? I hope you enjoyed the discussions what we had in today's class, right? Therefore, if you have really enjoyed the discussions, right, you don't forget to click like, share, subscribe, and comment to our YouTube channel. We'll meet in the next class with the design of compression members, right? Till then, bye bye, students.